Welcome to the SAR channel, where sound and audio are demystified. Linear PCM is the standard method for turning sound into digital form and is known for its high quality. Other digitization methods exist, each with their own pros and cons compared to PCM. In Linear PCM, the sound wave is represented using evenly spaced steps, while other systems use different or entirely new mapping methods. A main advantage of these special methods is that they often reduce the amount of data needed to store the sound. However, this efficiency can sometimes lower sound quality. In Linear PCM, the spacing between quantization levels is equal across the entire signal range. The number of levels depends on the word length. The longer the word, the more precise the sound. But more precision also means more data. Uniform PCM works best when the signal's amplitude is evenly spread out, yet most sounds are not uniform. To handle this, some PCM systems use uneven step sizes to better match the signal's characteristics and reduce distortion. Floating point systems change the signal's amplitude dynamically, helping capture both very soft and very loud sounds more accurately. Another variation called delta modulation, DM, takes a very different approach. It uses only 1 bit per sample but needs a very high sampling rate to work effectively. Floating point systems are a modified form of PCM that use a scaling value to adjust the signal level. This makes them an adaptive version of non-uniform quantization. In true floating point systems, the scaling factor changes instantly for every sample, while in block floating point systems, one scaling value is applied to an entire group of samples. A floating point converter uses several gain stages to adjust the signal's amplitude for the best analog-to-digital conversion results. This makes it especially effective for handling very loud or very quiet sounds. Although floating point systems have a wide dynamic range, it behaves differently from that of a fixed linear system and is actually smaller than the signal-to-noise ratio. The dynamic range compares the loudest possible signal to the noise when no signal exists, while the signal-to-noise ratio measures noise when a signal is present. In fixed linear systems, these two values are about the same, but in floating point systems, the signal-to-noise ratio depends mainly on the converter's resolution, not on the dynamic range. When the signal changes, the system's gain also changes, which can affect how noticeable the quantization error is. Sudden gain changes from one sample to the next can make the error more audible. To prevent this, floating point systems use algorithms that smoothly adjust the gain according to the signal's overall level. Gain can decrease immediately to prevent overload, but any increase must happen gradually to maintain clean, accurate sound. The main benefit of block floating point systems is that they reduce data size, making them useful for situations with limited storage or transmission bandwidth. They also work well with compression methods like syllabic compression. In this system, a short segment of the sound wave, for example 1 millisecond, is converted into digital form. A scale factor is then found based on the largest value in that segment, and the whole block is adjusted so the highest value is just below the maximum possible level. This process reduces the number of bits needed to represent the sound. When the data is played back, each block is scaled back to its original level. Unlike systems that change gain from one sample to the next, block floating point systems avoid most of the unwanted noise or distortion caused by rapid scaling. The noise follows the signal with a very short delay, about 1 millisecond, which is too brief for the human ear to notice. This makes gain changes almost inaudible. Block floating point systems work best with sounds that have a steady level and few sharp peaks. Instantaneous floating point systems handle quick, sharp changes better, but overall perform worse than fixed linear systems. However, this dependence on the sound's behavior is a common weakness in many non-PCM digital systems. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Let's continue. In Linear PCM, the spacing between quantization levels is the same across the entire signal range. Floating point systems create uneven spacing or non-uniform quantization by changing the range. Non-uniform companding systems achieve a similar result but use a different method. While compression is not the most precise way to create non-uniform quantization, it is simple and practical to implement. In these systems, large signals have wider spacing between quantization levels, while smaller signals have closer spacing. This helps improve accuracy for quieter sounds. The system works by first compressing the signal, boosting low levels and reducing high levels, before quantization. During playback, the signal is expanded back to its original form. This process, called companding, compressing plus expanding, helps reduce the amount of noticeable quantization noise. The mu-law and A-law systems are types of companding that use an almost logarithmic curve. They are commonly used in telecommunications to make 8-bit audio signals sound clearer and of higher quality. Differential PCM systems work differently from regular linear PCM. Instead of storing the actual values of each sample, they record only the changes between samples. This makes them more efficient because these differences are usually much smaller than the full signal levels, so fewer bits are needed. When the sampling rate is high, each sample is very similar to the one before it, meaning there's a strong relationship between them. DPCM systems take advantage of this similarity to reduce redundant data and use fewer bits to describe how the sound changes over time. This method can also lower quantization errors compared to standard PCM. Depending on how the system is built, it can use either uniform or non-uniform quantization. Differential systems use a technique called predictive coding. This method estimates the current sample based on previous ones, then encodes only the difference between the predicted value and the actual input. The predicted signal is subtracted from the real signal, and the remaining difference error is quantized. During playback, the decoder uses past samples to make the same prediction and combines it with the stored difference to rebuild the waveform one sample at a time. If the prediction is accurate and the error is small, fewer bits are needed to represent the audio. However, the system's performance depends on how well the prediction method follows changes in the signal. Compared to standard PCM, differential systems use simpler hardware, achieve better data efficiency, and are less affected by bit errors in a noticeable way. In differential systems, the difference between the input signal and its predicted value is encoded. When the sampling rate is very high, the changes between samples become smaller, allowing for finer resolution. Delta modulation is the simplest type of differential PCM. It uses a very high sampling frequency and only one bit to represent whether the signal goes up or down from the previous sample. Because each step is fixed in size, a fast sampling rate is needed to accurately follow quick changes in the sound. Delta modulation is simple and efficient in hardware design. It uses an integrator as a predictor that constantly adjusts up or down based on the input. At each sampling moment, the system checks whether the signal is higher or lower than the predicted value and moves one step in that direction. The accuracy depends on how large that step is. If the steps are too big, precision is lost. If too small, the system can't keep up with rapid changes. The decoder uses another integrator to rebuild the waveform. As in other DPCM systems, higher frequencies cause lower signal-to-noise ratios, about 6 decibels loss per octave. However, since delta modulation uses only one bit, large signal errors like those in PCM are avoided, though parity and interleaving are still used to correct smaller errors. In practice, delta modulation is not suitable for high-quality audio because it must balance between sampling rate and step size. Small steps improve sound accuracy but can't follow complex, fast-changing signals, causing distortion. While oversampling can help, the rates needed for full bandwidth audio are extremely high, for instance, around 200 MHz to match a 16-bit PCM system with 96 decibels signal-to-noise ratio and 20 kHz bandwidth. Noise is always present and most noticeable in quiet signals. Despite these issues, the high sampling rate in delta modulation does have benefits. Each time the sampling frequency doubles, in-band noise drops by about 3 decibels because the noise spreads over a wider range. This reduces the audible noise floor, and the high rate also means simple filters can be used instead of steep ones. Although delta modulation isn't ideal for high-fidelity sound, its improved version, sigma delta modulation, works much better and is widely used in modern AD and DA converters. The Super Audio CD, SACD format, for example, uses direct stream digital, DSD, a single-bit system based on sigma delta modulation. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Adaptive delta modulation, ADM, improves on regular delta modulation by changing the size of each quantization step. This helps the system follow fast signal changes more accurately while keeping distortion low. The encoder analyzes the input and adjusts the step size automatically. When the signal changes quickly, up or down, the steps become larger. When the signal alternates smoothly, the steps become smaller for better precision. This adaptive behavior increases the signal-to-noise ratio without needing a higher sampling rate or more bits. However, ADM systems are more complex to design. The decoder must stay synchronized with the encoder's step size adjustments to properly track the changes. Rapidly changing the step size for sudden audio peaks can be difficult. When loud, high-frequency sounds require large steps, quantization noise increases and the background noise level becomes uneven. It's also hard to add dither noise in ADM because the changing step size makes a fixed dither amount ineffective. Error feedback can help reduce noise in the audible range, and a preemphasis filter can make noise less noticeable in quiet sounds or mask noise changes caused by variable step sizes. Another version, called Continuously Variable Slope Delta Modulation, CVSDM, improves on this idea by allowing the step size to change smoothly instead of in fixed increments. In this method, instead of changing the step size like in adaptive delta modulation, the system adjusts the signal's amplitude before sending it into a fixed step delta modulator. This prevents overload and keeps distortion low. To further reduce quantization noise, a linear predictive filter uses data from many past samples to make a more accurate prediction of the next one. The companding system includes digitally controlled amplifiers in both the encoder and decoder. These amplifiers automatically adjust the signal level based on the bit stream to keep tracking errors small. They continuously change the gain to match the signal's strength with the modulator's fixed step size. A fast speed-up circuit allows the system to quickly lower the gain during sudden loud sounds. The rate of gain adjustment depends on how dynamic the audio is. Spectral compression can also be applied to balance the frequency content. It reduces high frequencies when they dominate the input and boosts them when low frequencies are stronger. This keeps the overall frequency balance at the AD converter nearly constant and helps maintain consistent audio quality. Adaptive Differential Pulse Code Modulation, ADPCM, combines the predictive accuracy of differential systems with the efficiency of PCM to reduce data size. A linear predictor, tuned for the specific type of audio signal, estimates each sample's value. This estimate is subtracted from the actual input to get a different signal, which is then quantized into a short PCM word and sent by the encoder. This process allows the system to automatically adjust to the signal and shape the noise in a way that keeps it below the audible level. The decoder works in a similar way. It reads the input data, selects the right step size, and reconstructs the signal by adding the differential data to the predicted value. A low-pass filter is then applied to smooth the output. A DPCM's main advantage is its lower bitrate, achieved by focusing the signal's amplitude and frequency content into a smaller range. In performance, ADPCM can match or slightly outperform standard PCM, producing less quantization noise while using fewer bits. Different versions of the ADPCM algorithm are used in many telecommunication systems and even in software and video games. Unlike complex perceptual coding methods, ADPCM encoding and decoding require very little processing power. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.